Hello everyone, I'm Zhang Wenqiang, a postgraduate student from the School of Information Science and Engineering at Nanjing University. I'm glad to attend this conference, and I will introduce our work, a malicious web request detection technology based on Git Recurrent unit. This presentation may consist of 4 parts: research background, proposed method, experiments, and conclusions. First, let's look at a report released by Symantec in 2019. This report is about network security. It said web attack on endpoints increasing by 56% in 2018, an average of 4,800 websites compromised with form jacking code every month in 2018. In total, Symantec blocked 3.7 million form jacking attempts in 2018. More than a third of form jacking activity took place in the last quarter of 2018, with 1.36 million form jacking attempts blocked in the period alone. In the past year, the development of the network makes a quality of increasing in network traffic. However, network threat has increased at a faster speed. Currently, the methods of network security traffic detection are almost signature-based or behavior-based. This page shows the typical characteristics of the two methods. The method we use in this paper is signature-based. For the behavior-based detection method, the token's team proposes to analyze requests of HTTP logs by data mining, then proposes a multi-port matching algorithm based on stream data analysis. For signature-based detection method, there are mainly the following methods. Method of the decision tree estimated the risk by Shannon entropy. Use the methods based on Markov model, but the accuracy of those methods is not high enough or have a limited target scene. The work of pre-processing is to extract the URL from the log or HTTP datagram and remove the domain name, port number, and other irrelevant information. Then we get a string like this. And next, we split the string. The method of split will explain in paper in detail, and then we get a word list. To make a word into a number, we need a dictionary to query its index. However, the number of words in the network request is theoretically infinite, and we can't build an infinite dictionary. So we need to limit the number of words in the dictionary. We performed a statistic of the training set of the CSIC dataset and found that the frequency distribution of words is like this. From the red part, we can see that a few words account for a great frequency. Let us zoom in all these parts, which is more intuitive. In fact, the core 450 words account for nearly 90% of the occurrence frequency. So our dictionary can be very small, such as only using more than 400 words. What about the words that are not added to the dictionary? We divide it to 7 categories that cannot be directly included in the dictionary, as shown in the graph, so that each category can be added to the dictionary as a word. We will get a very concise data input and remain the most of the information. So for our example, it will be like this. In the end, each word can find the relative index number in the dictionary and then encode it to get an array. This data still cannot be used for the neural network, because the neural network needs an array of the sameness. So we need to remove which too long and short ones need to pad. So what is the suitableness of the array? Then we made a statistic of the number of words contained in each item of the CSIC train dataset. The result shown in the blue part of the figure. We can infer that if the dataset is large enough, the next frequency distribution should meet a part of a Gaussian distributor. Therefore, we fit the Gaussian distribution, as shown by the red line in the figure, and then integrate the fitted curve to get the following image. By calculation, we can see that items with less than 130 words account for 99.5% and almost include all items, so 130 is a not bad choice. We know that the LSTM network is an improvement of RNN. This kind of network has the ability of memory that suits our feature extracted from the URL string. GRU is a variant of LSTM, which has a similar effect with LSTM by experiment. And GRU has a simpler structure and requires less calculation than LSTM. Our neural network structure is like this. It starts with the embedding layer, enters the GRU network, receives its output and input the fully connected neural network, and finally outputs the prediction result. The neural network of this structure designed to achieve higher recognition accuracy and lower computing resource consumption. Besides, the entire data and computing process can transplant to parallel platforms such as FPGA, GPU, multi-core processors. We used two datasets for experiments. The Information Security Research Institution of the Spanish National Research Council created the CSIC dataset. It contains multiple types and is earlier, although it has a lot of data items. When we remove the duplicates, and they become much smaller after sorting. XSSDS is an actual attack connected by ourselves and only contains a cross-site script as an attack type. From the experimental data, the XSSDS dataset has obtained an excellent test result because it only has one type of attack, and the data is reliable, and its loss curve also converges very quickly. For the CSIC data of various attack types and poor data quality, we also got good training results. Therefore, this technology has positive significance for malicious web request detection. Also, it should be noted that since the data of the two training datasets are derived from different services, the data is very different. And the form data dictionary is also very different, so it is not suitable for cross-validation. Each web service environment has a lot of relevance in terms of word composition, but less relevance for different web service environment. This makes it easier to detect its own data, but it is not friendly to other data. We will study how to reduce this dependence in the future. I have finished my topic. Thank you for listening. If there are any questions, contact me by email.